Hello again, APChem. This is Mr. Coker, and this is going to be the notes for Chapter 9. We're still talking about covalent bonding and orbitals, and this is the Zumdahl textbook 354 to 381. At the end of Chapter 8, we talked about the different shapes of molecules using valence shell electron pair repulsion. However, when you try to link up valence shell electron pair repulsion with the atomic orbital model of the atom, SP, D, and F, there are a lot of ways they just don't fit. For example, if we look at carbon in methane has 4 identical tetrahedral orbitals, but the carbon valence electrons are 2s and 2p. S orbitals are spherical, so they shouldn't really point in any one particular direction, and p orbitals have 90-degree angles between them, which does not fit the 109.5-degree bond angles in methane. So we have to have a type of patch on the localized electron model to explain the shapes of valence shell electron pair repulsion molecules. And the way we do it is we mathematically mix the s and p orbitals together. They are, in fact, mathematical wave functions. So if we blend s and p together, we get hybrid orbitals. The hybrid orbitals are somewhat shaped like mushrooms, and in the case of mixing an s orbital with 3 p orbitals, you get sp3, which is a tetrahedral, 4 lobes pointing tetrahedrally toward the corners of a tetrahedron. So this gives us the orbitals that we need. So we see it graphically on the left, top left. We see it with the energy levels on the right, the 2s and the 2p mixing to make the sp3 orbitals. Interestingly, you first have to excite the electrons for carbon to make it work, because carbon has to move an electron from the 2s to the 2p before you can blend it. This particular diagram is for nitrogen. Notice for nitrogen that one of the sp3 hybrid orbitals actually has an unshared pair in it, whereas the other 3 are used to single bond to hydrogens, overlapping with hydrogen's 1s orbital. So there we have NH3. In the case of CH4, we have all 4 of the hydrogens are sp3 hybrid orbitals between the carbons and the hydrogens. In the case of water, you have 2 of the sp3 orbitals are used for bonding to hydrogen, and the other 2 are used for unshared pairs. When you have trigonoplanar geometry, you have 120 degrees, so once again the s and p orbitals don't quite match up with the bond angles. So instead we will use sp2 hybridization. When we use sp2 hybridization, we get 3 sp2 orbitals, hybrid orbitals that point towards the vertices of a trigonoplanar triangle. We also have a leftover p orbital. That can actually help us with explaining double bonding. For example, in C2H2, shown in the bottom right, carbon is sp2 hybridized, but that can only explain one of the 2 bonds between the carbons, the one that is the red sp2s overlapping. We say when a bond is formed by atomic orbitals overlapping on a line between the 2 atoms that it's called sigma bonding. However, the p orbitals, in this case labeled pz, can also overlap where the p orbitals widen out at the top and bottom, so we can get some overlap up there, and that's called a pi bond. And so that actually explains both of the bonds between carbon atoms. in C2H2. In BF3, we actually use the 3 sp2 orbitals to make the trigonal planar shape. The p orbital then would not have anything in it. It would be unoccupied. SP hybridization is used for linear electron domain geometry. So when we want the electron pairs to be 180 degrees apart, we use SP hybridization. SP hybridization leaves you with 2p, actually a p orbital, a py, and a pz. So we're left with two, count them, 2 p orbitals left over. These can also be used for pi bonding. So in the case of C2H2 acetylene, we can have pi bonding above and below the sigma bond between the carbons, and we can have it in front and behind the sigma bonds. Pi bonding can also be seen in CO2, where you have horizontal pi bonding for one of the CO double bonds, and then the vertical pi bonding for the other CO double bond. Notice when a pi bond overlaps in two places, it only counts as one bond. We can also use hybridization to explain expanded octets. We simply mix in the d orbitals with the s and the p orbitals. Trigonal bipyramidal electron domain geometry uses dsp3 hybridization. So anything with the trigonal bipyramidal basic electron domain geometry, you can expect that to be dsp3. In the case of octahedral geometry, we need to mix 2 d orbitals with an s and 3 p's. So we end up with d2 sp3 hybrid orbitals. As you look at each of these types of hybridization, try to do the examples in the book as we go along. So this chart here summarizes the 5 types of hybridization: SP for linear electron domain geometry, SP2 for trigonal planar, SP3 when we have tetrahedral bond angles, DSP3 when we have trigonal bipyramidal, and D2SP3 when we have octahedral. Okay, so that wraps up the localized electron model. As you saw with the localized electron model, we did require a number of patches to the model, I'm sure some of you have had some issues with the idea of electrons being localized, since the whole atomic model of the atom shows electrons as spread out and smeared out in clouds. So to localize electrons are a bit of a concern with this model, plus all of the extra patches such as not obeying the octet rule all the time, and formal charge, and VSEPR shapes not always fitting the atomic orbitals, so we have to use hybrid orbitals and so forth, and resonance. So we have a number of patches. So you might be wondering, is there a better model? In fact, there is. As far as being more accurate, there definitely is a better model. It's called the molecular orbital model, or MOM, or MOM for short, and of course we know we can always trust MOM. So the molecular orbital model is a more trustworthy model. It does require some higher level mathematics because it is based on wave functions, but with supercomputers these molecular orbitals can be calculated. The basic idea is electrons, if we treat electrons as waves instead of particles that are localized in one place, if we treat them as spread out waves, then we can say that the wave of electron density from one atom overlaps the wave from the valence electrons of another atom. So in effect, what we do is we look at the physics of what happens when waves overlap. There are two ways that waves can interact when they overlap. One is constructive interference. If we take a look on the left side here, these blue wave pictures, we have wave A and wave B, and they are approaching each other. And when they meet, because they both have positive amplitudes, they're going to add and give an even greater wave. So if this is a wave function, that would mean a higher density or a higher electron probability where the two waves interact, or where the two clouds overlap. If in fact these waves travel through each other, they still retain their identities and will simply move right and left and move away. But that's not what we see with electron waves in atoms. They simply overlap and then stay overlapped. There is another way, though, that waves can interact, and that's called destructive interference. Destructive interference will create nodes or node density regions between the nuclei, which we call antibonding orbitals. So here we see A coming in from the left with a positive amplitude, and B coming in from the right with a negative amplitude, and then when they overlap, they in fact cancel each other out. So what we have with antibonding orbitals is where they overlap, the electron density actually goes to 0, or it's a node. So what does this look like for, say, hydrogen, H2, with 1s orbitals on each hydrogen atom? Well, if we overlap the 1s orbitals, as we see on the right side picture here, we would find that we would get one orbital where the electron density adds, and that's called a bonding molecular orbital. But we don't, and you show that on the bottom right. We also have anti-bonding molecular orbitals, which would have a node between them, because if the amplitudes do not match up in the same direction, you get destructive interference. So these both form. So you put in two 1s atomic orbitals from two atoms, and now you have orbitals that actually belong to the entire molecule, called molecular orbitals. And they are actually going to be of two types, one with lower energy even than the 1s were to start with, called sigma 1s, sigma because the type of overlapping is along the line between the two nuclei, and then sigma 1s star, or sigma 1s antibonding, which has a node. Now if you think about the node, it's actually going to put most of the density behind the nuclei and try to pull the nuclei apart. So it's not even neutral to bonding, it's anti-bonding, it's against bonding, it's pulling the nuclei apart. So we have one orbital that tries to pull the nuclei together, and we have another one that tries to pull them apart. Now the same rules apply, Aufbau principle, Hund's rule, and Pauli exclusion principle to molecular orbitals that apply to atomic orbitals. So in the case of H2, the two electrons in H2 would actually both occupy the bonding orbital. So you'd have two electrons that are bonding and no electrons that are anti-bonding. So in that case, we would say, based on the calculation, that the bond order is 1. We have 2 bonding electrons minus 0 antibonding electrons, so 2 minus 0 is 2. Divide by 2 electrons per bond, we would say that H2 has a bond order of 1, or that H2 is single bonded. So that's basically the molecular orbital model applied to the simplest of molecules, H2. It shows that the electrons can lower their energy by bonding, and that is the bond energy that we see for H2, the lowering of the energy of the electrons. And we see that the overlapping of the electron waves causes constructive interference in the case of the bonding molecular orbital. There's also destructive interference for the antibonding orbitals, or antibonding orbital, singular, but it is not occupied, so it does not apply in H2. In helium-2, however, it would be occupied because helium-2 has 4 electrons. So if helium overlaps its 1s electrons with another helium atom to try to make an He2 molecule, we see the diagram in the lower left. 2 of the electrons in He2 would occupy the bonding orbital, the sigma 1s, and 2 would occupy the antibonding, the sigma 1s star. So our bond order would be 2 bonding electrons minus 2 antibonding electrons, which is 0, divided by 2, which is 0. So He2 does not form a bond. So we see that this model actually works very well for helium-2 and hydrogen-2. It explains the behavior of both molecules. So then we get into the second row with like lithium 2 and beryllium 2 and carbon 2 and nitrogen 2 and boron 2. And we see that the overlap of the orbitals becomes a bit more complicated. So let's take a look at how the orbitals would overlap in the second row. Now the two s orbitals would overlap quite similarly to how they overlap with the 1s's. You would get a bonding orbital where constructive interference between the waves occurs, and an anti-bonding orbital with a node, which we would call sigma 2s star. Our p orbitals actually overlap two different ways. The px's would overlap end to end because they would both be pointing horizontally. In that case, you're going to get constructive interference, and you'll get what we call a sigma 2p, and that's shown in the bottom right where we have a lot of blue there with the sigma 2p that's bonding electron density, pulling the two nuclei together, lowering the energy. But we would also have, if the amplitudes do not match up, we would have some anti-bonding orbital, and so we would have the majority of the electron density pulling the electrons or the nuclei apart, and that's called an anti-bonding or a sigma 2p star. The py's and the pz's would actually overlap the way they show in this box here. If you overlap them in a way where the pluses and minuses align, you would get what we call a pi bonding molecular orbital. So the bonding molecular orbital, which lowers the energy, would be due to pi overlap between the p orbitals, just like we saw earlier with the multiple bonds overlapping p orbitals. We would have pi bonding, but we would also, if the pluses and minuses are opposites, we would have pi antibonding orbitals, which kind of look a little bit like a butterfly with the middle part missing. That's a nodal plane in the middle. So the antibonding molecular orbitals would try to pull the nuclei apart, and the bonding molecular orbitals would try to pull them together. Now just notice there's more than just one pi bonding and one antibonding pi. There's going to be two, because this kind of overlap occurs with py and py, but it also occurs with pz and pz. This is what the diagram looks like for the energy levels of these molecular orbitals, starting with the sigma 2s and the sigma 2s star being the two lower ones. Notice in lithium 2, the sigma 2s bonding orbitals are filled and the sigma 2s antibonding are not. In fact, if you vaporize lithium metal, you will actually have Li2 molecules, single bonded. So that's kind of interesting verification of this molecular orbital model. Notice the sigma 2s's energy decreases as you go from lithium to fluorine, and that is because more protons in the nucleus pull those 2s electrons in tighter, which we've talked about in the periodic trends discussion. The sigma 2s star, the antibonding orbital, begins to be occupied in Be2, so there is no Be2 molecule because the bond order would be 0, 2 bonding sigma 2s electrons and 2 antibonding sigma 2s stars. In the case of B2, for B2, the pi 2p are actually lower in energy than the sigma 2p. In this particular case, they've decided to make the sigma 2p subscript z. Not sure why they do that. I would have called it sigma 2px and the other two pi 2p y and z, but you can pick your own coordinates. The two electrons are going to occupy the pi 2p x and y. Notice they are unpaired, which would give this B2 molecule some paramagnetic properties. In other words, it would respond to a magnetic field and be attracted. In the case of C2, the same pi 2p x and y are occupied doubly. Hund's rule kicks in. You get 1 and 1 in B2, but you get 2 and 2 in C2. So in the case of a C2 molecule, it would actually have a double bond because it would have 4 bonding electrons that are not canceled by antibonding electrons. N2, of course, we know is triple bonded, and that shows up with the pi 2p and the sigma 2p, all 3 molecular orbitals being filled with a pair of electrons. So it has 3 sets of bonding electrons. In the beryllium through or lithium through nitrogen region, there's actually some interaction between the 2pz and the 2s, which causes the 2pz, sigma 2pz, or I would have called it the sigma 2px, to be higher in energy. However, that interaction is lessened in O2, and in fact, sigma 2p is lower energy than pi 2p for O2. You might wonder, how do they know this? In fact, PES graphs of PES data on these molecules can verify these different energy levels by using PES. So O2, very interesting example here. 2 electrons in a sigma 2s, which are canceled out by 2 electrons in a sigma 2s star. 6 electrons in the bonding sigma 2p and pi 2p's, and then 2 unpaired electrons in the pi star or pi antibonding orbitals. Those 2 unpaired electrons get paired up in F2, and then of course if we showed neon 2, it would fill up the sigma 2pz. If we calculate bond orders here for Ne2, you would get 0, F2 would be 1, O2 would be 2, N2 would be 3, so it has all the right bond orders, or single, double, triple, no bond for the molecules is verified by this molecular orbital model. Focusing in on that oxygen O2, sigma 2s, sigma 2s star, sigma 2p, pi 2p's, and then the pi 2p that are unpaired, the paramagnetism of liquid oxygen is shown by pouring liquid oxygen between the poles of a powerful magnet. As seen on the left, there is an attraction there, and that's called paramagnetism. See, the localized electron model has no explanation for the paramagnetism of liquid oxygen. I know it's kind of a rare property you wouldn't think much of, but it is a case where you have a model that can't explain a phenomenon. There is no reason in the localized electron model to believe that oxygen has any unpaired electrons. If you question me on that, just draw the Lewis structure. You'll find out all the electrons are either shared pairs or unshared pairs. However, oxygen obviously has unpaired electrons because it is attracted to a magnet in a way that things, molecules and atoms with unpaired electrons should be. The molecular orbital model shows this simply by putting 2 unpaired electrons in equal energy pi 2p stars. Molecular orbital models can also be used on heteronuclear diatomic molecules or different atom diatomic molecules. Below we see nitrogen monoxide. Now in the case of nitrogen and oxygen, they have orbitals that are fairly similar in energy and size. So you have something that mimics quite closely the mixing of atomic orbitals in homonuclear diatomics. The case of NO helps us understand, okay, what do we do with that case where you have nitrogen monoxide and you have an odd number of electrons? The molecular orbital model has no problem with that. It puts 2 electrons in a sigma 2s bonding, 2 electrons in a sigma 2s antibonding, 4 electrons in pi 2p bonding, 2 electrons in sigma 2p bonding, and 1 electron in a pi 2p star up above there. Now the labeling of these are a little different than the ones we used, but this is the best picture I could find of NO molecular orbitals. So their numbering system and so forth is a little bit different than ours. But basically, you show that the s orbitals, they cancel out. You have 3 bonds from the pi and sigma 2p bondings and 1 electron in an anti-bonding pi 2p star. So if we look at our bond order, that would simply mean that we have a 2.5 bond order. So there's no problem with a 2.5 bond when you have NO. The localized electron model, it struggles with it and tries to make it a triple bond or a double bond and can't decide which one, and you have to have a resonance and so forth. But this is just fine. We have a 2.5 bond because we have 6 electrons that are bonding and 1 electron that's anti-bonding in the 2p portion of the molecular orbitals. Over on the right, we see what happens with hydrogen and fluorine. Now H and F, we're going to overlap the 1s of hydrogen with a p orbital from fluorine because that's where the unoccupied orbital is on fluorine. However, because of fluorine's extra protons, fluorine pulls its electrons in tighter and has a lower energy. And so we find that the bonding orbital, which would be sigma, the sigma bonding orbital for HF is closer in energy to fluorine, and the antibonding orbital is closer in energy to hydrogen. So we could interpret this based on electronegativities that the bond would be closer to the fluorine atom, and in fact that's what we see when we have polar bonds, is that the 2 electrons in the bond are drawn closer to the atom with a higher electronegativity. In this case, fluorine's electronegativity is higher than hydrogen's. Finally, this idea of delocalizing or spreading out the electrons and not strictly following the localized electron model, this can actually be fairly satisfactorily applied back to the localized electron model. Now, we're not ready to scrap it. It's got a lot of uses. Even though the molecular orbital model is more accurate, it still can be patched. And one way we can improve on the localized electron model is to add in a concept called delocalized pi bonding. So this helps us with those p orbitals that are overlapping. The delocalized pi bonding is the idea that the p orbitals might not just be between 2 atoms, but maybe more than 2 atoms can share an area where the p orbitals overlap. One way of looking at it is with O3. With O3, if we consider all 3 oxygens to be hybridized in a way that gives them leftover p orbitals, you can see that there would be 3 ways that those p orbitals could overlap. If they overlapped completely constructively, you would get bonding orbitals, and we see that on the bottom there, where you have bonding molecular orbitals. If you overlap in a way that is anti-bonding up the very top, then you would get pi star or pi anti-bonding. And then there would be a third way you could actually overlap 3 p orbitals. You could have the right and left oxygen be opposite, and then the middle one could then overlap with one of them in a constructive way and overlap with the other one in a destructive way, and that would be called non-bonding, a non-bonding orbital. In fact, in O3, the bonding and the non-bonding orbitals are occupied, but the anti-bonding orbitals are not. Top right here in blue and red here, we have nitrate NO3-, which has a double bond and 2 singles when you draw its Lewis structure, but of course it would have 3 resonance structures. Those 3 resonance structures could be summarized by the picture in letter B, where the N's and the O's all have p orbitals that overlap above and below the NO3 trigonal planar structure. We also see trigonal planar for C2 or C6H6 benzene, and trigonal planar, of course, is going to be sp2 hybridized. So on the left here, letter A, we see what the sigma bonds would look like in benzene, C6H6. However, there are also p orbitals that stick up above and below the plane of the hexagon of carbons, and those p orbitals can actually overlap all the way around the hexagon there, and we call that delocalized pi bonding. So that completes chapter 9.